we agreed in the previous part of this topic that to calculate enthalpies of reactions, there are three sources of data. One of which was from board energies, and I hope we can calculate enthalpies given board energies. Now the other source of data will be empirical data from experiments. You want to calculate enthalpies of reactions from experiments. Now, and that is what this the next few subtopics will be all about, because in the next subtopics we'll be calculating the enthalpies of combustion, the enthalpies of neutralization, displacement. A solution also shall be included from empirical data, from experiments. Now, before I even get to the specifics, I want to underline one thing, that it is going to be very difficult to determine the amount of energy that is produced by a given reaction. That is what I mean. Supposing I get a piece of magnesium ribbon and then I burnt it. How do I get the amount of energy that that piece of magnesium ribbon is producing? So it is going to be very difficult to determine the amount of energy that is produced by the burning magnesium, for example. Because supposing I brought a thermometer here. I brought a thermometer here. What would be the accuracy of the thermometer, for instance? Yeah. So when I put the thermometer there, of course it's going to overshoot and it's going to expand so much because a lot of energy is going to be produced and then it's going to burst. It's very difficult to determine that. Now even think of a very simple experiment like the reaction between sodium hydroxide and hydrochloric acid. I want to isolate the sodium hydroxide. Here we are, 1 gram of that, and the hydrochloric acid, and in this case maybe hydrogen chloride, and then measure the amount of energy that is being produced by that reaction. I think I have told all that. I have a very big, it's a big task. But that task is simplified by ensuring that what I actually measure is the amount of heat that is absorbed by the environment. The amount of heat that is absorbed by the environment. So in all cases, the environment is going to be either water. Yeah, the surrounding is going to be either water or solution. So like our difficult and almost impossible task here. I can just get the magnesium, burn the magnesium, use the energy to heat some amount of water. Then I can get the amount of energy that is absorbed by the water. But now see, water is not the system under study. The system under study is the magnesium. So water becomes the environment, but it is absorbing the heat. So the assumption shall always be that the amount of heat that is produced by the burning magnesium is equal to the amount of heat that is absorbed by the environment. And not, even if I do this experiment, put the sodium hydroxide and hydrochloric acid, and then I put it there, the thermometer is not part of this system. The thermometer is part of the environment. So energy is going to be taken from the environment or absorbed by the thermometer, which is a part of the environment. So this shall be our underlying assumption in all the calculations. So you have to identify the surrounding, the environment, so that you can get the amount of heat that is absorbed by the surrounding. Then from that, you can equate that to what was produced by the reaction, and that will make it easier. Now, so there are several steps that shall be involved in the calculation of enthalpies with that underlying assumption. Step number 1. So the first thing that we shall do is determine the mass of the environment, the mass of the environment, the mass of the water, all this solution that is absorbing the energy, all that is producing the energy for an endothermic process. Then you'll have to work out the temperature change of the environment. Then, but note that the temperature change shall always be given in Kelvin. That is a convention. The temperature change should be given in Kelvin. But the temperature change in Kelvin is always equal to the temperature change in degrees Celsius. I have seen some students making mistakes by first subtracting. Like if the temperature changes from 23 to 32, that is at 9 degrees Celsius change in temperature. Now, but some students now remember they were told to always give the temperature change in Kelvin. So what do? They immediately get very fast to that and add 273. Then that they get to 282. That is completely wrong. That is completely wrong. If you want to work in Kelvin, you need to convert each of them to Kelvin. So 23 plus 273 to give 296. 32 plus 273 to give 308. Then you subtract them, you get 9 Kelvin. So the temperature change in Kelvin is equal to the temperature change in degrees Celsius. So you can just work in degrees Celsius and just put K there. So you don't add the 273 after you have subtracted. And that is important. So the first thing, get the mass of the environment, fine. And that shall be exactly where we are going to be using this question if you are ever going to be. Because we can only work from the environment and not from the reacting substance. So get the mass of the environment, work out the temperature change of the environment, all the surrounding, and then after that, the third step, you calculate the amount of heat that is absorbed by the water or the solid. That is whatever that is making the environment. How do you calculate the amount of heat? Now there is something that is called the specific heat capacity. The specific heat capacity. What is it? And this value will be given. When I say 4.17 joule per gram per Kelvin, what do I mean? That to raise the temperature of 1 gram of water by 1 Kelvin, then I need 4.17 joules. That is the interpretation of what you call C, for the specific heat capacity. To raise the temperature of 1 gram of water by 1 Kelvin, I need 4.17 joules. And therefore it is easy to determine the amount of energy that is absorbed by the surrounding or by the water. Because supposing the mass of water was 2 grams and you raised it by 1 Kelvin, how much energy will that be? Of course, it is simply 4.12 times 4.17 times 2. So because for 1 gram it is that. For 2 grams, therefore, it's going to be 2 times. Now supposing you are raising it by say 3 Kelvin. Yeah, for every 1 Kelvin, it is that. So for 3 Kelvin, you just multiply. So if you have m grams of water, and you are raising the temperature by some value delta T, and note I'm talking about delta T, so how much energy will that be? It will be, of course, 4.12 times the mass times the delta times the delta T. So that is where I get to this mc delta T. And note in chemistry we don't talk of theta. We don't talk of theta. That one I think is used in physics or some other. Yeah, you use that in physics. Theta is used in physics, but you don't use theta in chemistry. It is mc delta T. So m, and I repeat, is the mass of water. C is a specific heat capacity that has to be given, and then delta T. Now, but what is going to be important is you ensure that if the specific heat capacity is given in kilograms, then m must also be in kilograms. That is the only thing that you need to confirm, that the units are the same. And then once you have done that, it will be very easy. Now let's attempt a simple example using that expression. Calculate the amount of heat required to raise the temperature of 100 cubic centimeters of water from 25 to 76 degrees Celsius. Yeah, and you are given the specific heat capacity as 4.17 joules per kilogram per 4,170 joules per kilogram per Kelvin. Now, so of course the amount of heat is given by mc delta T. Now let's get the value of M. Let's get the value of M. I have 100 cubic centimeters of water. So what is the expression for getting the mass? So the density is equal to mass over volume. I'm interested in the mass. So the mass is equal to density times the volume. That is simple class 3 or 4 work. So 100 cubic centimeters times 1 gram over cubic centimeters. That and that cancels. But this is in kilograms. So these need to be divided by 1000. That gives me 0.1 kilograms. So the kilograms. Now delta T, now you say that the delta T can be in degrees Celsius, but you just write K, yeah? So I don't have to add 273 to each of that. So delta T will be equal to 76 minus 25, and I think that is equal to 51 Kelvin. 51 Kelvin. 51 Kelvin of 51 degrees Celsius, which is equal to 51 Kelvin. So applying this expression, M 0.1 times, that is kilograms, times what is this? 4170 joules per kilogram per Kelvin. Multiply that by 51 Kelvin. The Kelvin and Kelvin cancels, the kilogram and kilogram cancels. Whatever I'll get will simply be in joules, and I can convert that to kilojoules. And what does that come to? It's simply multiplied by 0.1, which is 417 joules, or 0.417 kilo, small k, capital J's. And that is simply how you go about it. So the idea is always to ensure that the units are the same. If it's in kilograms, then this must be in kilograms. So you'll get the energy in joules, therefore. So everything will cancel and you get the joules. And I think that is also very important. So that at the end of this expression, because this was given in joules, whatever you get here will be energy in joules. So that is the other step. So what have you done? You have managed to calculate the temperature change. You have gotten it. You have the mass of the surrounding, and you have actually calculate the amount of energy that is absorbed by the surrounding. So what is the next step? The next step is to determine the mass of the substance that is producing the energy. Like say the energy is being I used 2 grams of magnesium ribbon to heat that 100 grams of water. So it is the magnesium that is producing the energy that is being absorbed by the water. Now, of course, the assumption shall be the amount of heat that is absorbed by the surrounding is equal to the amount of heat that is produced by the reactive substance. Then you work out from this amount, you can work out the moles, and then get to the molar. From this amount produced this amount of energy. So what about 1 mole? And that shall be easy. Let's do an example. Example reads 50 cubic centimeters of 0.1 molar silver nitrate was mixed with 0.50 cubic centimeters of 0.1 molar hydrochloric acid. So what is happening is a precipitation reaction. Silver ions and the chloride ions to form silver chloride, because silver chloride is insoluble. So the initial temperature is 22.5. That's for the 2 of them. but the temperature of the mixture becomes 23.33. So what is the first step? Get the mass of the environment, the mass of water or solution that is absorbing the heat. So when the thermometer, it's measuring the temperature of what? It is measuring, so what I took was 50 cubic centimeters of one of them, HCl, another 50 cubic centimeters of this, the sodium, the silver nitrate, yeah. So mix them, and I'm measuring the temperature of that. So if there is a change in temperature, it is a change in temperature of the mixture. It is a 50 and 50 that were initially at 50, then are finally at 23.33 degrees Celsius. So the 100 cubic centimeters is what is absorbing the heat. I've not isolated because I've seen some students now go to the extent of working out the number of moles. So 0.1 times 50 over 1 over what? Yes, over 1,000. Those are the number of moles multiplied by 36.5 to give us the mass of hydrochloride, the mass of hydrogen chloride. So that is what they want to use as the M value. Did you isolate the hydrogen chloride to measure its temperature? You did not do that. You measured the temperature over the resultant solution, initially at that and finally at that. So and that is the first step, is 50 plus 50, those are cubic centimeters, multiplied by the density times 1 gram per cubic centimeter. So that is equal to 100 grams. That is my M value. What is the next thing? Get the delta. Get the delta T. Delta T. What is delta T? From 22.35 then to 23.33. Let us make that correction, please, that this is not endothermic. We should be subtracting the other way around, so that eventually whatever answer we'll get will be negative. You'll have a negative enthalpy change. What is that variable? 0.98 Kelvin is my delta T. That's my delta T. So I have the M, I have the delta T, and what now do I need to get? The amount of heat. The amount of heat that is absorbed by the surrounding. What does that amount to? That is mass 100 grams MC. Let's write the expression MC delta T. M is 4.18 joules per gram per Kelvin times that, M value is 100 grams times 0.98 Kelvin. Kelvin cancels, gram cancels. I can just multiply the rest. .64, what are the units? Those are simply joules. Now, so that is the amount of it that is absorbed by the environment. But that is absorbed from the environment. By how much? Now let me use one of them. Let me use either the silver hydrochloric acid or the silver nitrate, because they are equal amount, and the reacting ratio is 1 to 1. When you write the equation, so 1000 cubic centimeters contains 0.1 moles. That is what it means by 0.1 mole. What about 50? 0.1 over 1000 times 50, and that gives me 0.005 moles. So this is the number of moles that produce this amount of energy. So now let me write here for the sake of 0.005 moles produce 409.64. So what about 1 mole? .81928 joules, which can be converted to kilojoules by dividing by 1000. 81.928 kilojoules per mole. That is now per mole. So the units now changes from just kilojoules to kilojoules per mole. Then it's mad. Let us make that correction, please, that this is not endothermic. We should be subtracting the other way around, so that eventually whatever answer we'll get will be negative. You'll have a negative enthalpy change. I get to that. I can draw an energy level diagram for that process. So note the steps before I draw the energy level diagram. Note the steps that I started with. Get the mass of the environment. Very important. And this is where many of us will get it wrong. Because at any one time there are so many choices. I told you there are students who will choose to work out the mass of hydrochloric acid, the mass of silver nitrate. I don't know where they'll get the silver from. They have memorized that it's 1 weight, so they'll work it out and then use that. Those exact mass of silver nitrate, exact mass of hydrochloric acid, and the map, then use that. That is wrong. There are others that will just take one of them, either the silver nitrate or that is again wrong, because you need to follow your thermometer. Unapima temperature nini? Temperature. What temperature are you measuring? That is Greek. Someone unapima temperature is speaking in Greek. So you follow your thermometer. Look at the surrounding. The thermometer is part of the surrounding. What is it surrounded by? What is it surrounded by? Get the mass of that which is surrounding the thermometer. Once you've done that, you are... Ladies and gentlemen, if there is something that you need to take note of, it is that statement. What is the thermometer surrounded by? That is it. If you can always ask yourself that question, then you'll never get it wrong. So, the very first enthalpy that we need to calculate from experimental data is the enthalpy of combustion. Now, all of us know what combustion is. Burning. Burning is what we call combustion. And in combustion, a substance needs to be reacted with oxygen. It needs to bind with oxygen. So, and I said from the beginning of this topic that the definitions are important. So let's define enthalpy of combustion. So when you talk about any enthalpy, it's supposed to be per mole. So what do you think enthalpy of combustion is? Remember to include the quantitative aspect. So it is the amount of energy that is produced, and if you're not sure of that, you can always say the energy change when. But we don't have an endothermic combustion process. You can imagine something is burning, and then you move next to it, and you feel cold. Hey, I think you'd run away. You are trying to warm yourself and it is feeling cold. That will be metaphysics. Not really physics, but metaphysical. It is something that you need to revisit the grandfathers, black magic, white magic, and red, green magic, so that they can explain such a phenomenon. Okay, I've heard of a burning bush that is not being consumed, but we are not told it was feeling colder. We are not told. I don't think we've ever had a combustion that is endothermic. Anyway, that is another story for another day, for another subject anyway. But so combustion is exothermic. So it's the amount of energy that is produced when 1 mole of a substance is completely burnt in excess oxygen. So it has to be complete combustion. Note, I can burn carbon to form carbon 2 oxide. I can burn carbon to form carbon 4 oxide. So the enthalpy for this reaction is not going to be the enthalpy of combustion of carbon. Why? It has not burnt completely. This is not complete combustion. If I burn methane to form carbon 2 oxide, that is not complete combustion, because I am not getting when you burn carbon completely, it should produce carbon 4 oxide. So that eliminates that. So, and it has to be burnt in excess oxygen. Of course, when you burn in excess oxygen, that means you're going to have complete combustion. Now, but what about the standard enthalpy of combustion? Standard enthalpy of combustion of a substance is the amount of energy that is produced when 1 mole of a substance is completely burnt in excess oxygen under standard conditions. Where standard conditions refers to a temperature of 298 Kelvin under 1 atmosphere pressure. So I will talk of delta H combustion, delta H theta combustion, or delta H naught combustion. So this stands for the standard enthalpy of combustion of the substance. So it has to be under standard condition. So when you burn under standard conditions, all the measurement must be measured at whatever you are going to measure must be at 298. So for instance, when I burn methane in air to produce carbon 4 oxide and water, if I want to get the standard enthalpy of combustion, then I must measure at 298, in which case the water is going to be in liquid state and not gaseous state. So if I measure and yet the water is in gaseous state, then that is not standard. That is not standard, because at standard conditions, you must, if you want the standard enthalpies, you must always measure at the same temperature and pressure, and that is at 298 and 1 atmosphere pressure. Of course, you realize that if you get the water in gaseous state, the enthalpy is going to be different from when you get the water in liquid state, because you get the water in gaseous state, when you convert it to liquid state, some more energy is going to be given off. That is the enthalpy of vaporization. The reverse of the enthalpy of vaporization, when the vapor condenses to, so more energy is going to be given off. So this, it is going to be, so the actual, when you talk about the delta H standard of combustion of methane, it is equal to the combustion first. So this, to form gas, let me call that delta H1, to form the water in gaseous state, plus the delta H of vaporization, plus the delta H of vaporization. So it's going to be higher than that. It's going to be higher than that. So that is the definition of the enthalpy of combustion. So my first assignment would be to determine the enthalpy of combustion, and that can be done experimentally. I have a clip that will help us to capture that. In the clip that you are just about to watch, I'll be determining the enthalpy of combustion of methanol. So what I'll do is determine the amount of methanol that will be burned, or to raise the temperature of 20 grams of water by 20 degrees Celsius. Now, what do you think are some of the things I need to capture? What are some of the measurements I need to make in the course of that experiment? I hope you are listing some things like, what do I want? I need to get the mass of methanol that will be burned. So I need to get the initial mass of the methanol and the lamp, because I cannot remove the methanol and burn it elsewhere. So I need a lamp and the methanol, then get its mass. Then that is the initial, and then after burning I need the final. So these two will help me to get the mass of methanol. Now I need to measure some mass of water, and I've specified that it's 20. So I'll get some mass of water, measure that mass. Okay, let it be 20 cubic centimeters, because that's what I'm using now. Then the initial temperature. I need to make that measurement. I need to measure the initial temperature. Then as I carry out the experiment, I need to note the time when, I don't need the time, I just need to ensure that I stop the heating when I have raised the temperature to x plus 20. If I have continue to, you note that it's necessary to stir so that you can have uniform, the temperature can be distributed uniformly. Look at the color of the frame produced by the burning methanol. It's important to note that it is yellow and luminous. That means that there are some unburnt carbon particles. That would be a source of error, because that would be incomplete combustion of methanol. So what other sources of error can you think of? Now, using the data that you have obtained from that experiment, let us proceed to work out the enthalpy of combustion. Use the data obtained to work out the enthalpy of combustion of methanol. So the first thing is to get the mass of methanol that have been used. And that, of course, is 1 gram. The change in temperature is, of course, 20. The change in temperature is 20. So first, we determine the mass of the environment. Now look at your thermometer. Where is the thermometer? What is the mass of the surrounding, of whatever surrounds the thermometer? Is it 1 gram? Whatever is surrounding the thermometer, is it 1 gram? I think it is 20 cubic centimeters. So our M is equal to 20 grams. If you get that, you are almost there, my friend. Now, what about delta T? It is 20. So, what is the amount of heat that is absorbed by the environment? So, heat is equal to mc delta T. Mass is 20 grams. So, let's use 4.18 joules per gram per Kelvin. But it will be given, and the change in temperature is 20, 4.18 joules per gram per Kelvin. So 20 grams, the mass of the whatever surrounds the thermometer, 4.18, the specific heat capacity, times 20, this is in kilogram. The kilogram, the Kelvin cancels, the gram and gram cancels, so I can get the amount of heat. There is 1672 joules. Now the next thing, get the amount of the amount of methanol that is reacting. It's 1 gram. I can convert that to moles. Methanol CH3OH. There is a mass of water 12 plus 4, 16 plus 16, 32. 32 grams for 1 mole. So 1 gram is how many moles? Zero 0.03125 moles is what is producing this amount of energy. So 1672. What about 1 mole? So that amount of energy in joules, kilojoules per mole. Kilojoules per mole. What is the sign? It is negative. Negative. There is an increase in the temperature of the surrounding. So that is what I get. So what are the steps? Get the mass of the surrounding. Follow your thermometer. The delta T that was given in that experiment. Then get the amount of energy that is produced during that reaction. And then by what amount, because you want to go per mole. You want to get to per mole. So by this number of moles, and what about therefore 1 mole? About 1 mole. But when you get to that, it is per mole on the side. Now the next thing we are asked to do is to write the thermochemical equation. I can remove all this. Methanol burning to produce carbon 4 plus water. Okay. What's 1 carbon, 4 hydrogen. How many oxygens do I have? I have 4, I have 3, so I can write 3 over 2 there. That equation is going to be balanced. So this is negative 53.504 kilojoules. And I can even write per mole because it's per mole of methanol. Now an energy level diagram for the same. It's exothermic, so they are lower. Methanol plus 3 over 2 oxygen to form CO2 plus 2 H2O. Energy. Time. That is the energy level diagram for that particular reaction. Next question. Hey, the difference between the theoretical negative 720 kilojoules per mole and 53. That's a very big error. It's a very big error. But where does that come from? Now, number one, there is a lot of heat losses. A lot of heat losses to the surrounding body. So if you press your hands near the burning methanol, you press them near, would you feel warmer? Of course, yes. Why? Because the air around is being heated. There's radiation there. There's heat loss by convection. Convection. So there's evaporation, some very energetic particles are, and then there is a heat loss by conduction. So if you're not careful, you touch these, you will really burn, you get burned. Why? So because these apparatus are also absorbing heat. So there is heat losses by conduction, which can be minimized by ragging. There is heat loss by radiation, which can be minimized by using, cover with a cardboard. Let that experiment be done inside a cardboard. You'll prevent the draft, the weed, the interaction, the weed interacting with that. You will prevent that. So we call that a draft shield. Then you can cover, maybe use a star, cover it to reduce the amount of convection that is taking place. So there is all those heat losses. Now the second source of that error is the nature of the frame. So that as the methanol was burned, it was producing a yellow frame. What does that mean? Some unburned carbon particles. Unburned carbon particles, we were told in Form 1, unburned carbon particles that grows. So unburned carbon particles means incomplete combustion. So you do not burn all the methanol to carbon 4 dioxide. So incomplete combustion will lead to another source of error. But that is what we can get from that particular experiment. So is it an experiment you can set up and do? Yeah, because you just need to, because you can be asked to describe an experiment that can be used to determine the enthalpy of combustion of sulfur, for instance. Can you discuss with somebody? Describe an experiment that can be used to determine the enthalpy of combustion of sulfur, and show it to your teacher. Another example that we can look at and attempt, 1 gram of sodium was completely burnt in excess air. Yes, so it's a solid that is being burnt. The energy that is produced used to heat 400 cubic centimeters of water. The temperature rises from that to that. Calculate the relative atomic mass of M. Given all that data. So how are we going to go about it? Of course, we need to get the amount of energy that is absorbed by the water. So where is the thermometer? Let's use our MC delta T. So where is the thermometer? What is it surrounded by? 400 cubic centimeters of water. So 400 cubic centimeters, so 400 grams times, C, 4.2 joules per gram per Kelvin times the change in temperature. We can subtract that. Kelvin it is, gram, so what does that give us? Yes, so that is the amount of energy that is produced. Produced by what? By 1 gram of that. 1 gram of that. But you can also get this number of moles. You can convert this. Now we know that 1 mole produces this. So these are how many moles? Eh? So 363 kilojoules. So we need to convert that to joules. Joules is 1 mole. So 3072 joules is how many moles? This number of moles, that is what is equal to 1 gram. So 1 mole. No units for relative atomic mass. That is basically what we can do in that question. Probably we can apply whatever we've learned to work out the enthalpy. Calculate the heating value of ethanol. I think that's a new one. So the heating value of a substance is the amount of energy that is produced per gram of that substance. So you could start by working out the molar enthalpy of combustion of ethanol, and from that get what about 1 gram of ethanol. Just attempt that, compare your answer with somebody. So the next thing that we shall look at is the enthalpy of solution.